Okay, in this video, we're going to go over how to free body diagram a mass on an inclined plane. The way I'm going to go about this is by doing a quick review of some basics. First, one-dimensional vector. A one-dimensional vector refers to a vector that points either up and down or left to right. The reason we call those one-dimensional vectors is if we kind of try to analyze those, we would need to use kind of a coordinate system, and when we do so, you'll notice that that's only going to be in the y, and that's only going to be in the x. And so that means a two-dimensional vector would be something that kind of looks like this. Okay, and if we try and analyze that one here, once again, we establish a coordinate system, and you'll notice that that is a combination of x and y. The other thing I want to review is some vector addition. So how do we add, two one-dimensional vectors? If I'm trying to add something like this in one dimension, which would be like traditionally the x, to something like that in the y, the way we do that is we go ahead and draw one vector on the tail of the other tip, and what we get is what we call the resultant vector. Okay, so we get this two-dimensional vector out of it. One thing I want to kind of emphasize is that we can take a two-dimensional vector and write it as a combination of two one-dimensional vectors. That's really what we're doing. And that's the idea, that this vector can be written as a combination of two one-dimensional vectors, one that's going this way and one that's going this way. Okay. Now, as for a mass on an inclined plane, what I want to go over is, let's take a look at a mass on a surface. Something like that. And some things that you want to define is what we call a normal. The normal is this line that's perpendicular to the surface of contact, and it's always going to be that. And if we kind of draw our weight here, you'll notice that the weight is right in line with the normal. Okay, so what we're going to do is we're going to start, really kind of inclining this, and we're going to see what's going to happen to the weight and the normal. So if I put it on an incline here, you'll notice that there's going to be this, the weight will kind of still pull it towards the center of the earth, but the normal is actually going to be at this angle, and there's the angle that we're looking at the incline. And you notice that there's going to be this angle here that's going to start, growing. And if I go ahead and do that again, you'll see once again that as I increase this angle, the angle between the normal and the force of gravity is also increasing. And if I do it to an extreme amount, now of course that's still going to be perpendicular, an extreme amount, you'll really see that the angle between the force of gravity and the normal is the same angle as the angle of the incline. So that's the idea. So how is that going to help us analyze a mass on an inclined plane? So here's my mass. We're going to go and start with something that's stationary, so it's not moving. Okay. Here's my angle. So we're going to go ahead and free body diagram this. We're going to start with the first one. This is going to be a first iteration. We're going to call this the weight. Now this thing wants to slide down this way, but it won't because friction is opposing this thing. We'll call that the force of friction. And this thing's not falling towards the earth because the table is pushing back on that, and that's what we call the normal force. All right, so we can analyze, that's our first iteration. There's our forces on the object, okay? Now, when we're trying to establish our coordinate system, what's going to help is kind of looking at it like that, right? So if we look at it, our coordinates like that, you'll notice very quickly that if I establish a regular x and y, that we end up with these two-dimensional vectors here, and we only, only the weight is going to be one-dimensional. So what usually helps is if we line up our y with our normal, and when we do so, what we've done is we've reduced the force of friction to a one-dimensional vector, the normal force to a one-dimensional vector. And so the only two-dimensional vector I have to worry about is that weight, where this would be one of those vectors and this one would be the other. So if we kind of set up our coordinate system like that, then we would be able to see that this is going to be the y component and that would be the x. And we just call it that. And so we can go ahead and redraw our free body diagram by kind of rotating this whole thing. And I'm going to go ahead and do that. So my second free body diagram is going to look something more like, I still have my normal force, but I'm going to put that straight up. I have my force of friction, which is going to be pointing this way. I'm going to replace the y, this weight, with its y and x components. The y component is going to be pointing down this way. And the x component is going to be pointing this way. Now I'm going to analyze this triangle a little bit more. So I'm going to redraw it. And this is what we call W. We have this thing that's going to be WY. And then this one's going to be WX, where this is our theta. Now if you look at this here, we can use a little trigonometry, and you can prove it to yourself, that y component of the weight is equal to W times the cosine, since it's the side adjacent, and WX is equal to the W sine of the angle. So there's a few things we can do here. Usually this would be acceptable as a good free body diagram. We can also plug in WX here. We could call that W sine theta. You might also remember that W is equal to mass times G, and mass times acceleration, but just not any acceleration, it's the acceleration of gravity. So we can even plug that in here. So we can even go WY is equal to M times G times cosine theta. And Wx is equal to m times g times sine theta. And we can also plug those into our free body diagram if that's what we want to do.